The word transmutation means atoms changing into different types of atoms. Now, of course, transmutation doesn't happen in chemical reactions, because in a chemical reaction, whatever type of atoms and how many you start with, that's what you have at the end. It's just to whom they're bonded is different at the end than at the beginning. But in a nuclear reaction, atoms actually change into different types of atoms, and we call that transmutation. And when we say transmutation via radioactive decay, we mean that there's no outside bombarding particle that is required to start this thing. It just happens spontaneously. Whenever we're balancing nuclear equations, the mass, which is on top, and the charge, which is on the bottom, have to balance on each side of the equation. And we'll show you a couple of examples of that. So let's cover alpha decay. Here's an atomic nucleus. What happens in alpha decay is an alpha particle is spit out of the nucleus. There's an alpha particle. It doesn't matter which I've colored which, but the protons are one color, the neutrons are another color, and you can see that an alpha particle consists of 2 protons and 2 neutrons. It's a chunk of the nucleus that consists of 2 protons and 2 neutrons. The alpha particle, which is actually the same thing as a helium nucleus, is quite massive for a radioactive particle, much more massive than a beta particle, which we'll talk about in a little bit. And because they're so massive, they move relatively slowly, and they don't penetrate human skin. Here's an example of a radioisotope that undergoes alpha decay. The mass of an alpha particle is 4, because it has 2 protons and 2 neutrons. The charge is positive 2, because of the 2 protons. And then we can either write He next to that, or you can write the symbol for an alpha particle. Sometimes it's written 4 over 2 with this little alpha, sometimes it's written He. They're equivalent. What's left? The mass has to balance on each side, on top, and the charge has to balance also. So the mass that's left is 230, because on the left we have 234 for the mass, which equals 4 plus what, so that's clearly 30. Down on the bottom here we're going to have 90, because again the bottoms also have to match up. 92 on the left, 2 on the right, plus 90, and if you look on the periodic table, element 90 is thorium. It turns out, not just for this specific case, but for any alpha decay, you always end up going down 2 numbers on the periodic table. Whatever element you start with, after an alpha decay, you're 2 elements lower than that. And you can see that here. We've started at uranium, which is element 92, and we've ended up at thorium, which is 2 below at element 90. What about beta decay? There again is our radioactive nucleus. A beta particle, I've tried to indicate there, is much faster moving, and it's much tinier. And that's because a beta particle is actually just a fast-moving electron. It has very little mass. It penetrates the body a little bit more than alpha radiation does. Let's give an example of an isotope that undergoes beta decay. The mass goes on top. So what's the mass of a beta particle? Well, what's the mass of an electron? Basically 0. Charge on an electron is -1. That goes in the denominator, you might say. It's not actually a denominator, but you can think of it that way. And then let's put a little symbol there. How about a little b for beta particle? Or you could write it with an E for electron. Those are equivalent ways of writing that. Let's figure out what's left. The mass is easy to figure out. Clearly that mass is going to be 234. Now be careful with the bottom, because it's very easy to write 90 down there, but 90 is wrong, because on the bottom, on the left, we have 91, which must equal -1 plus what? Not 90, 92. So be very careful with that. That is the element uranium. So anytime you undergo beta decay, you go up 1 number on the table. You can see that we started at protactinium, which is element number 91, and we ended up at one element higher, uranium. Alpha decay, you go down 2 numbers. Beta decay, you go up 1. In beta decay, the effect is that a neutron is converted into a proton, ejecting an electron from the nucleus. Here is the representation for a neutron. It has a mass of 1, and it has no charge, and I put a little n there to represent neutron. If we eject a beta particle, which is an electron, electrons of course have no mass and a charge of -1, what must be the other product? On top we must have a 1, and what must we have on the bottom? Also a 1. What particle has a charge of +1 and a mass of 1? Well, shoot, that's a proton. As a note, there are no electrons in the nucleus, we believe. The ejected electron is formed when energy released from the nucleus congeals into mass via Einstein's relation E=mc². Let's summarize. Here we covered transmutation, the changing of atoms into different types of atoms via alpha decay and beta decay. An alpha particle is a slow-moving chunk that flies out of the nucleus and consists of 2 protons and 2 neutrons. In alpha decay, we go down 2 elements on the periodic table. A beta particle is a fast-moving electron. In beta decay, we go up 1 element on the periodic table.